I didn't think that we would have this good weather, but that's good in a supposedly non-vacation week, but some people think it's a vacation. We welcome you all this morning for the defense of a PhD in the Department of Plant Protection, the section of entomology. I have my student Alan Sofan, who took his master's in the same department here. And actually he has been with us since 2007, where he took his master's, and now hopefully he's finishing his PhD. He took his bachelor's in Jawatingga. And who doesn't know, Jawatingga is the central Java in Indonesia, and in the city of Yogyakarta. And that's the University of Gajah Mada University. It's a very famous university. I visited that university. Supposedly the top 3 universities in Indonesia. Alan, during his time in the King Saud University studies, his master's and PhD, he published so far 11 papers. And that's not normal for graduate students, but I think this is a benchmark for many of the students here. He won 3 prizes as a KSU student. What's that? Symposiums. 3 times he got the prizes, and he got another 4th prize as a second level for the scientific excellence through the Deanship of Graduate Studies in our university. And this is very good, and so many of our students in our department and in our college have gotten many prizes, but I don't think they got 4 in the period that they've been here. I'm happy to introduce him, and I'm happy that you are all here, and I thank the committee members, especially Professor Arnab, who came far away from KAUST to be a member, Professor Yusuf Ibrahim, Professor Saleh Al-Dosari, Professor Mohammed Tufail, and myself. I would like him to start, please.
Assalamualaikum warahmatullahi wabarakatuh. Welcome aboard. So first of all, I would like to say thank you very much for the department, of course, to the committee defense, and to the supervisors who made this seminar possible. And of course, it is honor for me to be here among of you to present my PhD works entitled Molecular and Functional Characterization of Major Odor Receptors involved in the red palm beetle, Rhynchophorus ferruginus, aggregation from reception. I will start my talk with this picture because honestly, it has really impressed me. This is kind of tradition here, Saudi people, when we go to our friends Saudis, we will be served with the kohwa. And of course, it won't be delicious without baked fruit. And such tradition actually has an economic value because the resulting continuous demand. And this situation, we cannot find it in other countries. In my country, Indonesia, we only eat once in a year, the date fruit, which is in Ramadan. So, it is not difficult for us to find date palm tree in Saudi Arabia, and it is encouraging people here to grow and grow the date palm tree, and it led them to be the 3rd ranked world producer. And of course, when we see the date palm tree more and more, actually we are creating what we call a favorable environment for the organism other than human to enjoy the date fruit. We call it, in our perspective, we call them as pests. You know, it is actually not fair to call them pests because they want to enjoy also the date fruit. But we call them pests, and one of them is, we call it Rhynchophorus ferruginus, or Susa in Arabic. And it is very easy if I bring you now to the farm, and it is very easy to find such symptom. We call symptom that the trunk is hollow because of this red palm beetle. So, and this question is still relevant until now, either for scientists or the farmer, how to control the palm field. Actually, the key rule is simple. Once we know the key element of survival, then we can hit them. Of course, it's not an easy job, but at this time, we would like to focus on the olfaction, because this is one of the key elements of survival for insect. And olfaction means it is ability of any organism, not only insect or human, even protozoan, bacteria, they have olfaction mechanism to sense and to discriminate thousands of chemical odor in their surrounding environment. And of course, if we talk particularly for insect olfaction, we talk about the ability of male Lepidoptera to find their mate female that releases sex pheromone 10 kilometers away. Just imagine that. I don't think human can do that. What do you think? 10 kilometers away to find our wife, those who married. But I think it was before. But now we can do that through the GPS tracking system, right? So I think we can do that. So the question, are we different? 100 years ago, people start to talk about olfaction system. Now, 1911, Buck and Axel got the prize for characterizing the OR in mammalian. And only after 8 years, they know that insect is different. Different, of course, in defining 10 kilometers away of their mate, of course. And also the protein. Here in mammalian, we have simple protein, single protein. And in insect, there should be two proteins. First is OR, second one is what we call olfactory co-receptor. And if you notice in detail, the orientation of the protein is quite different, even opposite. The N-terminus is always intracellular or cytoplasmic, and the C-terminus always in extracellular. In future, is it important to study the OR? Yes, it is. There is one of the scientists in Japan. They tried to, identify the protein and identify the gene that encode the protein. They made what we call biosensor. They call it olfactory receptor-based biosensor. So they put the gene inside the cell lines, for example, head cell, and then they put something to record the potential difference because of the odor excitation, and they put it in just as little as chamberware. And just imagine in airport to sense drug smuggling, you don't need sniffing dog anymore, for example. You just put these simple devices and you will get the result. So I think that is enough for introduction. Let's go back to my PhD work. So as I said before, dead palm tree which is collapsed is due to the infestation of one of them by red palm beetle. And how they infest? Because it was mediated by the pheromone or aggregation pheromone. How they utilize this? Of course, because they have nose like us. But what is nose for insect? The nose for insect is antenna. And antenna, it is like nose for us, okay? There is a hair-like structure that we call sensilla. This is sensilla, the hair-like structure in the antenna. Then, actually it is complex system, but in general, in sensilla there are many pores which allow the other molecule to get inside, and there is OBB protein that will catch them to transport this to another protein that we call OR and ORCO for another process that we call signal transduction. This is very critical step. Once it finishes, then there is another protein to get rid of the molecule, then it will go to the brain for the specific behavior. So here, I will try to emphasize one of the critical steps in insect olfaction, which is the signal transduction. Simply, it is transforming the chemical molecules from the environment, then transform into electrical message, which will be processed by the brain, and brain will do something and will say that you have to avoid because it is predator, or you have to get in because it is your host, for example. So we are interested in this protein because it is doing the signal transduction. And what we are going to do in our objective is two things. We would like to characterize them. through what we call this internal transcriptome through next generation sequencing. And of course, we will try to make it more practical by silence the system. So we hope that after we silence the system, then the complete olfaction ability will be silenced, and they will not able anymore to find the host, to find the mate, and finally the population will be decreased. This is what we try to make a wish, something like this. So how we achieve this objective? Mostly our material is the antenna, because antenna is the nose. Right? Then two strategies were employed. First is constructing CDNA library. Here we collaborate with the cows, and there is Dr. Arnab here. So we went there for CDNA library, and we process. We are using their Illumina HiSeq. Then of course we also have collaboration with Jaxi from Ljubljana University. And after that, after we got the data set of antenna transcriptome, we are interested also to find, is there any specific OR which is particularly responsible for aggregation pheromone. That's why we are doing the functional assay using Excel. Second strategy is we are using CDNA synthesis, normal one, and we are calling the ORCO, the complementary of OR. So this we do the silencing through the RNAi, and we confirm through the several validation like EAG, then olfactometer, and of course through QRT PCR. So this is the core of our result. So we will have 4 points. First is OR hunting and etc. So in OR hunting, mainly we use this machine, the top one. This is next generation sequencing Illumina, which is present in the cows. And then we try to have some discussion here. And this work has been published in JMC genomic paper. And as you see here, if we this is the profile of our transcriptome data. If we compare with the closely related species, it is very clear that our data has more coverage. Probably we have better data. Of course, raw rate is more and content is more. We also have a more unique sequence compared to another one. And also from the annotated sequence, we are able to recognize 76 OR. This is all the compensation regions, OBB, CSV, CMP, gustatory receptor, and IR. And when we put, our sequence also hit it in the top, very close to the dead drop nodus, which is very close species. And also the most abundant mRNA is pheromone binding. This is one of also the most important in the antenna. And if we compare our OR, because now we are specific to the OR, we have another chemosensory, but we focus on the OR because OR is one of the most important protein. If we compare to this huge phylogenetic tree, our sequence actually were fit completely in this previously established system, which is having 7 classes. Even we propose another 2 sequence additional sequence, which is not 2 additional group, which is group number 8 and group number 9, and it was published in BMC. And another issue, if we try to make a tree by comparing them with another specific OR, the closely related OR, we will find interesting thing that the more pheromone receptor, which is already functionally characterized, were grouped together. This is all, for example here, this is Austrinia, this is Ceropetis, this blue tail line, so they are grouped together. And also, we also incorporate another megacellin OR, which already functionally characterized, and we found some of our gene, which is in red, also in the same clade. Same thing with another functionally characterized of MCAR20. We also have another content. From this one, then we conclude that maybe those 3 OR from another insect which already functionally characterized, which has very close relation with our OR, has the same function, maybe for aggregation pheromone. That's why we go to another experiment about functional assay. And this, we try to test 4 of them with the 2 main component of aggregation format, which is 4-5 and 4-5. And this is the general procedure of functional assay. We are using Hexel system, and the main thing is we just put all the OR and ORCO together, and we expose them to the stimulus, which is aggregation pheromone. And this is the typical result. And unfortunately, we found that our candidate is actually irrelevant with the ligand that we are testing. After functional assay means the story about OR, one of the protein is finished. Now we are moving to the ORCO, the complementary. Then we start with the characterization of the ORCO, and we interested also to find the difference with 2 related species of Phrygianus, which is Phrenodotus, that we got from Indonesia. So we got Phrenodotus from Joliplan, Indonesia, and Saudi Arabia. And this work is published in PLOSMA. So when we compare both structure, both actually has very similar. There are 99.5 identity of the amino acid, and they are completely unique in the antenna, the ORCO. Then, when we put into the software, it is definitely true that there are 7 transmembrane domains. And as you see here, color means the amino acid which is different with other group. So we found there is many non-color. It means they are highly conserved G-ORCO among the different insect. And as you see, N-terminus is inside in cytoplasmic, and C-terminus is the outside, which is the typical of ORCO characteristic. And as you see here, the Calmodium binding site is exactly 100% similar with other related species. That is the transmembrane. How about if we put ORCO, this particular protein, with other ORCO available ORCO of another insect? Very interesting, because as you see here, color, it is exactly same as according with the conventional taxonomy group. All the same group, all the ORCO belong to different species, were in the same clade in the order level, like conventional taxonomy, or based on morphology, something like this. And you see here, Curculinidae also were in the same clade, and our sequence is here with Pherogenes and Phrenodotus. That's the characterization of ORCO. Now we try to make it more practical. How about if we silence this ORCO? Because in the beginning we say that ORCO is one of the proteins which is very important for signal transduction for the smelling purposes. So this is the procedure, general procedure. We are injecting the double-stranded RNA into the pupae, and in the pupae, when they are emerging as adult, we collect the antenna, and we did some validation. First is the first validation is through QRT, and this is the result. Visually, you see here the ORCO. The first and 2 is the first is non-injected group. We didn't inject anything. We call it NI. And we will use it throughout the experiment. And second is nucleus free water injected group, and this is the double-stranded RNA injected group. And as you see here, we didn't find the ORCO expression compared to the tubulin, which is supposed to be which is expressed in all the group. And we found there were 96% expression reduction in the double-stranded RNA injected group, which is quite good compared to other work. When we try to raise this question, how long does the ORCO gene stay silent? We make a setup of experiment. We set up 10 days, 21 days, 35 and 60 days after injection. We call it post-injection. And we found that in all these different periods, the suppression of the ORCO expression is persisted. And this actually told us many things. First of all, it told us that the double-stranded RNA that we produce actually has systemic effect, because we are injecting in the dorsal part of the abdomen, and actually the target antenna in front. So it can go there. It went there for targeting the ORCO. Second thing, it can long last up to 60 days. We inject in pupae, and 60 days after injection, the expression of the expression is still there. So it is good. But actually, in another group, even it can be inherited to another progeny. It's really interesting. Then next we will do second validation, which is more practical. We are using live individual. In previous we are using antenna. Now we are using live individual. And this is the setup. And this is, you see here, the first result. This is dealing with the red polyfield, which is not injected. It's normal individual, and 70% going to the stimulus. Compared to the injected, only 20%, and most of them has no response at all, 56%. And if we calculate statistically, those stimulus which going to the stimulus is significantly different between the non-injected and injected one, and the control also significantly different. The third validation is using EAG. This is the real setup, and we have the schematic setup. So we are using computer, and there is signal devices, and also stimulus controller, and there is an antenna for preparation. And we put antenna here actually. We cut the antenna of red polyfield, and we put it here, and there will be another odorant that we spray here for stimulus excitation, and we will record it through the appropriate software. And this is the typical waveform produced by the activity of antenna when we expose them to the different type of stimulus. We are using 3 types of stimulus: pheromone 1, pheromone 2, and ethyl acetate. And this is the control. Control means non-injected. So, as we are expecting, all of them has a response. They are giving waveform. While the silenced one, the individual which is silenced, they don't have any response to any of tested chemical. And statistically also true that both those which is silenced, this one, also significantly different. So, what will be the next? Until at this step, we are scientifically confident that silencing has significant effect to the one of the most important activity, which is smelling activity. The insect cannot be able to smell. And the next is, there are many papers actually discussable. This one of them is published in 2007 in Nature. Actually, the majority of the author belongs to the company, so maybe there is some economy aspect. So they try with the corn. They try to make double-stranded RNA to be expressed directly into the plant system. So here, corn non-transgenic. It means this corn cannot produce the double-stranded RNA, and this one is transgenic, which produces the double-stranded RNA. So here there is significant difference that the transgenic crop free from the pest. While another interesting things, because silencing, gene silencing or double-stranded RNA work is also not only in our field, in agriculture, it also had been done in medical particularly. And this is another interesting review. This is how they try to make a delivery system, and this is a typical of non-viral. So they try to put the double-stranded RNA or siRNA in cholesterol or in lipoplex, liposome, etc. for delivering into the human. So, and of course, this is very interesting that they have been already for commercialization. You see, there are several companies which is already focused and develop this kind of treatment. Even for the cancer, the tumor, the HIV, now they are in the clinical trial. So whatever advance that made in the medical science, actually we can adopt it, I think. So this is something which is encouraging for us for those people who are working in the gene silencing. And of course, we will try to highlight, to call back what we had been reached. First, we are already able to develop a data set of N-terminal transcriptome, including 76 ORs with some of them for sure has a function for the decreasing pheromone, but of course we need more experiment to prove that. And also our methodology to silence the ortho has 96% reduction in expression, and we are confident scientifically to say that this typical work is a promising means to control B field. Then this is our published paper, and also we are preparing other papers. And finally, I would like to say, extend my acknowledgement thanks to my PhD supervisor, to Dr. Rahman, Dr. Biru, Dr. Professor Saleh, and to committee member, Professor Yusuf, Professor Anna, Professor Tufir, and our collaborator in Lund University, Professor Lister, in Kaus, Dr. Anna and Anal Gedi, and in Ljubljana, Johannes Jacks, and in Gajah Mada University, Dr. Richard, and also for the former head department, Professor Azam, and current one, Professor Al-Nafer, and of course to my beloved teacher. I have been here for 2007, so of course I have a lot of interaction with them. Dr. Al-Kani, Dr. Soebani, Dr. Al-Tawi Al-Mutlaq, Dr. Syahwan, Dr. Maulan Al-Hazmi, Dr. Saleh, Dr. Amjad, Dr. Khawaza, Dr. Omar, Dr. Saleh, Mr. Amin, Samin, there's two Samin here, so Dr. Yasir and Dr. Komi and etc. which I cannot mention. And of course, significantly the support that I got during my here, studying here, Dr. Abdul Hasmi, Dr. Shubha, Dr. Shami, Sugeno Murid, Khalid Sejat, Arya Koko, Mr. Iqbal, and all Indonesian brothers which come here and all the time supporting me. So thank you very much for your attention.